Hello everyone, welcome to a fresh new lecture on the topic Introduction to Frequency Domain Signal Processing for the course on Signal Processing Algorithms and Architectures. This is Dr. Anirban Dasgupta and let's get started. So, while understanding the topic frequency domain, let us first understand what is frequency. What is frequency? Now, if you have studied in your school day physics, it is something like the number of cycles per second, and in the context of signal processing, I would like to define it as the number of cycles a sinusoidal signal completes per unit time, usually in 1 second. And this is typically measured in the unit hertz, where in 1 hertz how many sinusoidal cycles are completed. Now, people often get confused with two terms. One is the frequency content and the fundamental frequency. And of course, these are different things. So, what is the difference? So, if we see these two signals, now these two signals you can see that in 1 second there are 50 complete cycles, but the difference is that one is a sine wave and the other is a square wave. So, both have the same fundamental frequency, which is 50 hertz and which is obtained by 1 by time period, but the frequency content of these signals are different. What does it mean? So, fundamental frequency, if you see, is the lowest positive frequency of the periodic signal, and frequency content refers to the distribution of frequencies that make up the signal. For example, how many such sinusoids of different frequencies are present in the signal is referred to as the frequency content of the signal. So, if you see these graphs, there is a sine wave of 50 hertz, there is a square wave of 50 hertz, there is a sawtooth wave of 50 hertz, and there is a triangular wave of 50 hertz, and all have the same fundamental frequency, which is 50 hertz, but these are made up of different sine waves or combination of different sine waves, and the frequency of those sine waves which make up this signal is called the frequency content, and this introduces us to the Fourier analysis, that how to know the frequency content of a signal. Like as I said, frequency content refers to the different frequency components that constitute the signal. Now, if we perform a Fourier analysis on a signal, then we can get the fundamental frequency and the harmonics, which are basically multiples of the fundamental frequency, and these signal collectively form this complete signal. Like for example, if we pass white light to a prism, it breaks it into the constituent frequencies. Like if white is passed, we get the Vibgyor components. Similarly, in Fourier analysis, if we send a signal, all the components of the signal, which are nothing but sinusoidal waves varying at different frequencies, will be split out, and that is the purpose of Fourier analysis. Now, if the signal is periodic in nature, then specific number of sine waves, specific means there can be infinitely many sine waves also, but these sine waves are of discrete frequencies. Like say if one frequency is f naught, the other frequency will be 2f naught, and so on. That is multiples of the fundamental frequency f naught. And if it is an aperiodic signal, then we will have all possible frequency range from say negative infinity to positive infinity or 0 to infinity, whatever you say. So, we will all discuss these categories. So, the question is, what is Fourier analysis? So, this is just a mathematical technique to decompose such signals into the frequency components of which that signal is made up of. And why is it used? So, this is very much helpful to analyze and process signal specifically in the frequency domain. Like for example, in time domain we have learned some smoothing techniques, but technically say I have a signal which has some frequency content, like when I am speaking my audio signal will have a specific frequency content, whereas there is some background noise which may be of some different frequency range. So, by observing their Fourier analysis, then we can actually determine that which portion is my signal and which portion is noise, and we can easily filter them out. So, Fourier analysis, as I said, is that it is the principle which states that any periodic signal can be represented as a sum of sines and cosines which are at different frequencies. And there are two types of Fourier analysis depending on whether the signal is periodic or aperiodic, and if it is a periodic signal we have Fourier series, and if it is a aperiodic signal it is a Fourier transform. And to visualize this, the spectra is called a line spectra and a continuous spectra for your periodic and aperiodic signals respectively. So, what is a spectra? Spectra is just a fancy name for the frequency domain representation. So, we have a line spectra. Line spectra means suppose if I have a signal say sine 2 pi 10 hertz and plus sine 2 pi 20 hertz. So, in the spectra we can see that these two components are present, and this is a periodic signal, sum of two sines, and if you do the Fourier analysis we see that the 10 hertz and the 20 hertz components will be present. If I give some magnitude to this, like this is 4 times this and this is 5 times this, so 10 hertz will have a magnitude of 5 and 20 hertz will have a magnitude of 4. Of course, it will be split into positive and negative frequencies which I will discuss. So, line spectra basically is that. So, if you see this in the frequency domain, you see one at 10 and the other at 20, and similarly there will be something in the negative frequency also at minus 10 and minus 20. So, these are all lines, and the other thing which is the Fourier transform, which is for aperiodic signals, your spectra will be continuous. Now, there is a very nice mathematical explanation to this, that why it becomes continuous. So, if you closely see what is this spacing, say if I have your periodic signal, so there is an f naught, this is a 0, there can be some 0 frequency also, this is say twice f naught, this is thrice f naught. So, if you see this spacing, what is this spacing? This spacing is f naught, and what is f naught? F naught is the inverse of your t, t is my time period. So, now if we see as t reduces, what happens? This spacing will increase, and vice versa. If t increases, then my spacing will reduce. So, what happens in this case when t is tending to infinity? Then the spacing will tend to 0, this f naught spacing. What does it mean? This means that my time period of the signal is tending to infinity, that is my signal will repeat after infinite time, which means it will never repeat practically, and when it will never repeat, that means it is an aperiodic signal. And similarly, if the spacing tends to 0, that means now you no more get a line spectra, now the spectra will be continuous like this. So, that is continuous spectra for aperiodic signals, and hence you see that in the periodic signals where you have Fourier series, you get the summation term, whereas in the synthesis equation, whereas in Fourier transforms you get the integration term, because this is no more discrete amount of frequency components, they are continuous in nature. So, this is what I was talking about. So, if you see clearly that in line spectra or say spectra of a periodic signal, say if we have two waves somewhere near say 50 and 150. So, we see the magnitude spectra and there are components at 50, minus 50, 150 and minus 150. But in a continuous spectra for an aperiodic signal, we see that the frequency values are defined for all values of the frequency axis. Maybe if it is a band limited signal, you will have within certain range, otherwise it may not be band limited. Now, coming to some more interesting concepts like zero frequency. So, what is zero frequency? And people say that zero frequency is the DC component of a signal, and what does it mean? It means the average value of the signal. Now, typically when we represent a signal, say it is a sine or cosine, whatever it is. So, if you see the average, it is typically 0, and hence we do not have any DC component. But if we bias the axis such that we add something to this signal, then the signal shifts vertically up, which is I have already discussed in the time domain, that amplitude shifting. So, that is introducing this DC component or DC frequency to this signal. So, if you have a DC frequency, that means that the signal has a bias and it is not having a zero mean. And zero frequency, because the definition of frequency says that number of oscillations in a second or unit time. So, zero frequency will never oscillate, even if it is something like this, that means it is having a tendency to oscillate. But if it is totally straight with respect to the x axis or the time axis, so that means it is a zero frequency, there is no change in the signal, that is that component. And infinite frequency is the exact opposite, that means that in a unit time there will be infinite such oscillations, which means the signal will not proceed. And this happens when there is a sharp discontinuity or an edge in the signal in the time domain. And here you clearly see that there are infinitely many values at this specific time instance t naught. So, if there is an infinite frequency present in a signal, it typically means that there is a discontinuity at the signal. And this is technically very idealized case. In real case, you do not encounter such sharp transition in signals, but theoretically still this is useful for analyzing many signals. So, pictorially this is our zero frequency. If you see that the amplitude is shifted to +1 level, and this is my zero frequency component, this one value of this amplitude. So, this is a sine wave plus 1, while infinite frequency happens in a square wave, perfectly square wave, where at this instance wherever there is an edge, there is a sharp change. Sharp means very idealistically sharp change, where this value of time will have multiple values of amplitude, which means the signal is not proceeding further, it is oscillating at the same point. Now, some more interesting concepts like negative frequencies and complex frequencies. So, you can see that in the spectra there are both positive and negative frequencies, and specifically this is happening in real signals where it has a positive component and a negative component. So, negative frequencies can be attributed to the counterclockwise rotations of the signal. Now, if you recall simple harmonic motions, so a signal is found when there is a rotating magnetic field. So, there is some kind of rotations, and if you see, if you have a point, so if you draw a right angle triangle, so you can see that this height of this is basically telling you about the motion of the sign. So, naturally if you see the Euler's expression, So, here also you get that sine can be expressed as sum of e power I and e power minus I. So, these two are the complex components of the sine. Similarly, cos will also have a e power I and a e power minus I. So, these are comprising of the two frequencies, positive and the negative. And negative frequency is basically representing the time reversal of the signal. That means, if I have a signal like this, so which means that there is a positive flow of the wave, there is a negative flow of the wave. So, both the positive and the negative frequencies are present in such a signal. What about complex frequencies? The complex frequencies are basically frequencies which has a real part and which has an imaginary part. Typically, you see this in your Laplace, where there is a sigma and there is a j omega term, where your j omega is used for your Fourier analysis, which is your frequency, real frequency of oscillations, and sigma is a damping factor. Why this damping factor is used? Like we know that some Fourier transforms do not exist because of the convergence issue. So, by multiplying with e power minus jt, not jt, rather sigma t, you actually multiply it with an exponentially decaying function. So, you force a signal which is not absolutely summable or integrable to be absolutely summable or integrable, and that creates a plane, the S plane instead of a axis. So, this is bringing the concept of complex frequencies. So, that is, the complex frequencies will involve both oscillations and a decay or growth. So, if you see this beautiful animation, so this is the formation of your cosine and sine. So, if you see the height and this width of the graph, so this is actually giving you the instantaneous amplitude as this is rotating, and this is a unit circle. So, you see that sine square theta and cos square theta, their sum is 1 based on the geometry. So, this is rotating in the counterclockwise direction. Similarly, if I make it rotate in the clockwise direction, then you get the negative frequency field, which is the opposite of the positive. So, this is an illustration that this cosine wave of 100 hertz has a positive frequency component and a negative frequency component. Now, ideally you should have a single component in the spectra, but I plotted this in Python, where I used a window of my sine wave. Now, naturally you cannot plot the total sine wave because it is of infinite duration. So, because of this windowing effect, you get only two values or two magnitude which are spread, which are not exactly at the desired frequency point, but there is a spread. This is a windowing effect. So, this is again, if you recall the properties of your convolution and multiplication in time and frequency domain. So, when you are windowing this signal, you are multiplying with a rectangular function, and multiplying a rectangular function in the time domain means convolution of the Fourier transform of the rectangular function in the frequency domain. So, because of that you get a spread. This is windowing. So, next is the concept of phase. The question it answers is, can two different signals have the same spectra, and if yes, how will you distinguish that they are different if they are having the same spectra? Like say I have two sine waves, only thing is that this is sine 50 hertz t plus 45 degrees phase, and if I see the magnitude spectra, again this should be ideal peak, but because of this windowing you get a spread around the peak. So, these two magnitude spectra are exactly the same. So, by looking at the spectra I will see that they are the same signals. So, how do we distinguish? Using the phase spectra. So, that is another takeaway, that is when I say spectra, there are two components, because this Fourier analysis will give you a complex number. So, if I have a complex number, something like if I say z is a complex number x plus jy, so I can always plot the magnitude and phase. So, the magnitude spectrum shows how each frequency component is present. So, that is the magnitude of the frequency components. So, this is how you get the magnitude spectra, just by taking the magnitude. So, if this z is your complex number, then your magnitude is obtained by x square plus y square, and your phase is obtained by tan inverse y by x, which is the phase spectrum. So, by the phase shift, you can actually distinguish that these two signals have the same magnitude spectra, but different phase spectra. So, they have a lag within each other, and this is the argument function, which is nothing but the tan inverse. The next concept I want to discuss is the sampling frequency. So, the sampling frequency refers to the number of samples taken per second, and it is also measured in hertz. So, what is typically the sampling frequency? So, as I said, when I want to convert an analog signal to digital, what I do is I pick the samples at typically uniform time gap Ts. So, this is my sampling frequency, that how many samples of the signal I am collecting in 1 second, and this is very important to understand the conversion of analog to digital or continuous to discrete. And the important theorem here is the Nyquist-Shannon sampling theorem, which states that you should sample at least twice the highest frequency component or bandwidth of the signal to accurately reconstruct a signal from its sample, and this is done to avoid something called aliasing. So, this minimum sampling rate, which is at least twice the maximum frequency content, is called your Nyquist rate. Like for example, if you have a signal which is made up of frequencies up to 500 hertz, then you should at least sample at 1 kilohertz to accurately reconstruct the signal. But this is just the theoretical sampling rate. Practically, you should sample at least more than 4 to 5 times this highest frequency component. The next concept is aliasing, which I just discussed. So, what is aliasing? So, if you see this diagram, so this is a signal which has two sine waves. One is of 50 hertz and the other is of 150 hertz. Now, what is the highest frequency component? This is 150. So, my Nyquist rate should be 300. So, if I sample at 600, see I am still able to get the structure of the waveform. So, this pattern is somewhat captured, although if I sample at even further like 1000 hertz, it will be even better, or even say 2000 hertz, it will be very nice. But 600 is sufficient enough to capture the structure. But if I take samples at 200 hertz, which is you see less than my Nyquist rate of 300, then I do not at all get the signal structure. I get a signal which is very much different from my actual signal. So, this is called aliasing, and this is aliasing in time domain, that if say this is a wave. So, if I take just 2 samples, I just take this and this. So, I miss this curve. If I take 4 samples, I am very much capturing the curve. So, more samples I take, the better representation of my time domain original signal in continuous domain is represented. What is aliasing in frequency domain? So, the same thing can be seen in the frequency spectra. Like if this is the original frequency domain representation of the signal, so if I sample at 600, so I clearly retain both the components of the analog domain. But if I do sampling at 200, so basically this version is aliased into this. So, these two replica are indistinguishable, like say this low frequency version and the high frequency version has the exact sample points, and you cannot distinguish these two signals. So, This is called the folding frequency. So, folding frequency is the half sampling rate. So, this is where the frequency is basically folded, like see here, this is the folding frequency. So, if my sampling rate is say 200, my folding frequency will be half of this, which is 100. So, this is the maximum frequency that can be accurately represented in the sampled signal, and any frequency which is above the folding frequency will be aliased into one of the frequencies below the folding frequency. So, this is what happens. So, if this is your bandwidth of the original signal, then if it is like oversampled means greater than Nyquist rate, then we see there is a clear distinction or clear separation between the spectra. However, if it is less than the Nyquist rate, so these two samples overlap. And this brings us to the concept of normalized frequency. So, what is normalized frequency? This is the frequency with respect to or relative to our sampling rate. So, if f is a frequency of the signal and fs is my sampling rate, so normalized frequency, which is a dimensionless quantity because we are taking ratio of 2 hertz. So, this normalized frequency is in the range of minus 0.5 to plus 0.5. So, what happens is, because say maximum I can represent 0.5 fs, this is my Nyquist theorem. So, anything say if I have a frequency which is say 0.6 fs, so it will be aliased to some other value, it will be folded back in this range. Like if you have a signal with frequency 200 hertz and we are sampling at 1000 hertz, so my normalized frequency will be 200 by 1000, which is 0.2, and this is the meaning that this frequency is 20% of the sampling rate. So, you can go maximum 50% of the sampling rate. The next is concept of digital frequency. So, this normalized frequency is a digital frequency technically, but we also represent digital frequency or digital angular frequency in radians per sample, and this is twice pi into our normalized frequency. And since the normalized frequency can vary from minus half to plus half, so this digital angular frequency will vary from minus pi to pi. Now, technically when you will study this DTFT, that this will be periodic with this as the fundamental period, but for all analysis purpose this range is used, that minus pi to plus pi. So, this is what typically I have explained. So, like say if you have a frequency which is 100 hertz and if your sampling frequency is 1k, then you can easily find your digital angular frequency using this formula, which is 0.2 pi radians per sample. So, what are the applications of frequency analysis? So, in signal processing, this is used for designing filters and noise reduction. Noise reduction, I gave the example. Filter design, typically it is done in the Z domain, Z transform. In communication, we used in modulation and spectral analysis, and even in image processing like DCT is used for compression, like JPEG compression. You have used the file .jpg or .jpeg, which uses this JPEG compression. And then in feature extraction, this Fourier analysis is also useful to know whether the features are high frequency features or low frequency smooth features. So, these in a nutshell is the construct of this module that we will discuss next: Fourier analysis, then frequency estimation and power spectral density estimation, then we will study Z transform, and finally coherence analysis. Thank you everyone. Have a nice day.